Hello, guys and gals, and welcome to 5.2D Part 2. This is going to be the last video I make for this section, so I'm just going to do one more example with you just to make sure that we understand how to find reactant orders for individual reactants and for overall reaction. Okay? I'm skipping over the example that contains S2O8 and iodine because it's very similar to what we did in the last video. The only difference is for this reaction that I'm skipping over is that some of the data decreased the concentration instead of increasing it like what we're used to. That's totally fine, okay? The order of a reaction is not dependent upon if you're increasing the concentration only. It's just a matter of how are you changing the concentration. So you're solving for the order the same way. How did I decrease the concentration of iodine? Okay, well then what happened to the rate because of that? Did it change at all? No? Okay, then that would be zero order. Did it decrease by the same factor? Yes. Okay, then that would be first order. Did it decrease by the factor that I decreased by times or squared? No? Okay, then it's not second order, right? So you can go back through the notes and see that example if you need to, but I'm going to focus on the example which is going to be a little harder than what we've been doing. So I've given us a pretend reaction between three reactants, A, B, and C, okay? And I've given us the data for the rate and concentration information that we would need to solve for the order of each of these reactants. And so the question is, what is the rate law for this reaction? And remember, we cannot write rate law unless we know the actual orders of each individual reactant. Because if they're asking you for rate law, they are not asking you for A to the X. They're asking you to say rate is equal to K times A to the first or A to the second. They want an actual order there. And they will not accept it if you don't include the correct order for each individual reactant. So let's use this data and let's solve for the order of each individual reactant. Well, let's start with A because it's the first one and it's the easiest to start with. So I need two trials where the concentration of A is changed, but the concentration of everything else stays the same. Well, it doesn't change between 1 and 2. It does change between 1 and 3, and B stays the same between 1 and 3. And C stays the same between 1 and 3. Okay, cool. So I can use trials 1 and 3 to help me determine the order of the reactant A. So when I doubled the concentration of A, I can notice that my rate also doubled, right? And so which order tells us that when we double our concentration, our rate will double? That is first order. So if we were going to write this rate law, we could do rate is equal to K, A to the first. Or again, you can leave that 1 out because we can assume that it's there. I'm going to split this in half because I'll need that bottom section later. So we now know the order for A. Cool. Let's move on to B. I need two trials where the concentration of B changes, but the concentration of everything else stays the same. Well, the only one where B changes is the fourth trial. So let's see if I can find another trial where everything else stays the same. Between trials 3 and 4, B changes, but A also changes, okay? Between trials 2 and 4, C changes, B changes, and A changes. Ugh, I don't like that at all. But between trials 1 and 4, A changes and B changes. Well, what's going on? I thought that in order to find the order, everything else is going to have to stay the same, right? Well, sometimes they don't make your life that easy. I'm sorry. But in real life, I mean, sometimes it would just be too much to try to keep everything the exact same and do the reaction over and over and over again without changing anything except the one reactant, right? So sometimes you're going to get data like this, where two things are changed instead of just one. When that's the case, solve for everything else first and come back to that guy, because you're going to need to know the orders of the other reactants in order to make sure that you get that reactant correct. So let's skip B for now and let's move on to C. Let's find two trials where C's concentration changes, but nothing else does. Okay, so I can see that the trial changes between, or the concentration changes between trials 1 and 2, and everybody else stays the same. Cool, awesome. That makes my life much easier. But the rate doesn't change at all. The rate is the same between trials 1 and 2, even though we doubled the concentration of C. So which order tells us that doubling the concentration is not going to affect the rate? That's zero order, okay? So C is zero order. If we wanted to write it, it would look like this. That's always going to be equal to 1. So we are not even going to include it in the rate law, okay? Don't include reactants that are zero order in the rate law, okay? Now that we know that C, if it changes, is not going to affect our rate at all, and we also know how changing A will affect our rate, we can solve for B. So you can do any of these. I think that it's easier to compare trials 3 and 4 because you know exactly what's happening to A and you know exactly what's happening to B, and C stays the same, okay? So if we look at trials 3 and 4, we can see that A has doubled. A has doubled. So we would expect, if B stayed the same, okay, if we ignored B, we would expect to see the rate between 3 and 4 double as well. Okay, so if B was staying the same, the rate between trials 3 and 4 should now be 20. That should be the rate because we know that A is first order. So when we double A, what we should see is that we double rate. Well, this number here is way bigger than 20. So we know that B is not zero order, because if B were also zero order, then your rate would be 20 and you would be done, because it would have done exactly what it was supposed to do with regards to A, and nothing else would have happened. But that's not what we see. We see that not only has it doubled, it then doubled again. Okay, so the rate was doubled twice between trials 3 and 4. Well, we know that one of those doubles is because of A. A was doubled, so the rate doubled. So the extra double had to come from B. So our rate was doubled because of B when concentration was doubled. So which order tells us that when we double our concentration, we will see a double in rate as well, and that's first order. So both A and B are first order. So you can write it like that, or you could write it without the ones, because most often this is how you're going to see it. Okay? Here would be the rate law for this problem. And I wanted to make sure that I did an example like that on video for you guys, because that's going to be a little confusing when we get here, okay? So just make sure that if you come across some data where there is no constant variable, where you're trying to figure out how the order of a reactant, but everything else keeps changing too, well, go on and solve for everybody else's order first, where you do have constant variables, and then come back and take a look at how your rate should have changed versus how it did change. And that will let you know the order of that other reactant, okay? So I hope that this was helpful. Please send me emails if it was not, and let me know if you guys have any questions.